can start. If you're
Okay.
comfortable, we can start. Okay.
Okay, sure.
So, yeah. Hi, everybody. Welcome to the India ML Reading Group. Today we have with us Atif. He's a PhD student at IIT Kharagpur. He's done his master's from the same institute and also collaborated with researchers at Stanford University. His research interests include machine learning and theoretical deep learning. He is going to give a tutorial today on uh, data augmentation techniques and other deep learning practices. So his talk is titled "Spend Less Time Tuning and More Time Chilling." And Atif, over to you. I would request everybody else to mute themselves.
Okay, thank you so much for the introduction. Okay, so the title is a bit weird on the weird side, but these days deep learning papers, you need to have catchy titles in order to market your work well, so that it gets accepted at conferences. So this is kind of coming from that perspective. Um, Anyway, so what the idea about this talk is basically at the bottom of the slide, some tips and tricks for achieving good performance on any deep learning task. It's a very um, general techniques that I'll be talking about that you can use right now, and I'll be providing code and references for everything. So you can just directly copy paste that code and you can achieve. I can't guarantee, but probably like 1% up to even up to 2% improvement in performance. Okay. So is this good, Siddharth?
Yes.
Okay. Yeah, so moving on. So before we actually start off with the actual presentation, I just want to talk about some good coding practices that you should be following. Um, this actually helps you to prototype your experiments much faster. Okay. Because mostly, like if, for example, when we write papers and we have some hypothesis, the idea is that you take your hypothesis and you have to run it over multiple experiments. I mean, even if it's completely theoretical, you need to do some experiments, right? And if you want to do some experiments, you have a data set. You'll have different data sets. You'll have different models, but your hypothesis is going to remain the same, right? For example, let's say you're working on creating a new normalization layer. So the code for the normalization layer is going to remain the same, but how you integrate it into different models is going to be different. At the same time, you also have to take into account different data sets because you need to show that your method works across all data sets and models. So for that purpose, you need it's better to follow certain good coding practices so that this doesn't take a lot of time, this integration thing together. So the what I like to do, which has really helped me in improving my workflow, is OOP, obviously object-oriented programming, and my writing still inspired from the way PyTorch Lightning works. So if you're using PyTorch Lightning, good. If you're not, you should. And even if you don't want to, then you can follow these steps. This is plain PyTorch, and it'll really help you in improving your workflow. So the idea is you have a model.py file, okay, where you define a model class. Obviously, if you're defining a class, you need to define its constructor. So the init function is the constructor in Python. And then you have the forward function where you write all of that down. So I'm assuming that you're well versed with PyTorch. Okay, so in the forward function, you write how you want to perform the forward pass so that auto differentiation can work properly, can build the computation graph correctly. And then there are three separate functions: configure optimizers, training step, and validation step. So in configure optimizers, that's where I pass my optimizer, my scheduler, everything goes in there. And my training step is basically for each iteration, what should you be doing? Okay, so that goes into my training step and same for the validation step. So this is what my model structure looks like. Then we have the data.py. So in the data.py file, I create a class for my data module in which again I have a constructor. And then there are a few functions like prepare data setup, train data loader, val data loader. And in prepare data, you download stuff. In setup, you create the data set, and in data loader, you return the data loader that you want to work with. So you have the model, the data. These are the two main things. You can also have a utility.py file, but more importantly, there's this main.py file, and main.py file should be as least cluttered as possible, because that's where you are integrating your stuff. So you want to have blocks where you can just pick a block and add one back. So it should be as less cluttered as possible. And this is where you call all your classes, right? Or you create the objects and you call the classes. So over here, we are going to create the model object. So if you want, let's say, if you wanted to do ensembling, you could create multiple objects of the same model, pass different hyperparameters, and you could get many different learners, right? Then you have the data object. So you can create, again, for each model, you might want to pass different, uh, let's say, data augmentation techniques. So you can do that using this method, and then you can just run your code. So this is like a very bare minimum overview. If you use this, personally, I feel it improved my workflow and can help you out as well. But moving on to the actual presentation, and please feel free to ask me questions anytime during the presentation. Um, I would love to answer them. So we'll start from the basics. So we'll start from the initial of the pipeline, which is data augmentation, right? Then we'll go to optimization, and then finally we'll go to a few other things. Um, so first we talk about data augmentation. Now this is more geared towards vision, but you can also apply these things, apply the same principles for NLP as well. Okay. Now data augmentation. So this presentation, I wanted to talk about or give you certain things that you probably won't get articles on the web. Okay, or you probably didn't know about it. So we start off with trivial augment wide. So what this does is basically a method that is a successor of the rand augment method. So what is this rand augment method? The idea is that you have a bunch of augmentations. Okay, so let's say you have a bunch of augmentations. So the augmentations look like this. So let's say you have identity, auto contrast, equalize, rotate, solarize, and so on. So you have a bunch of augmentations. What rand augment does is it says pick any pick how many augmentations you want and what is the intensity of those augmentations that you want to apply. So it had two hyperparameters. They use this, and in every epoch they would apply different augmentation. They would randomly pick m number of augmentations and apply n amount of intensity. Now, trivial augment wide, what it does is that it says you don't need those hyperparameters. Okay, just randomly pick one at every epoch, and randomly pick one augmentation, and randomly apply. So between 0 to 255, 0 to 1, whatever you prefer, just apply some randomly uniform chosen value. And it turns out that trivial augment wide, applying these random perturbations actually improves upon the performance of rand augment without having to use any further hyperparameters. So no tuning is required. And I've also provided the code and the reference here. So in case you want to apply trivial augment wide right now in your PyTorch code, you can do this way. Okay. More importantly, if you want to ask a philosophical question, as in why are we doing data augmentation? Just taking a step back, not talking about trivial augment wide and this and that. Sorry. You are doing data augmentation because there are many factors, but one of the important factors is uh, perturbing images. So basically, adding noise into your images improves regularization. Okay. And you might have heard about this in deep learning a lot, that adding noise actually improves regularization. This also comes into the perspective of optimization where you have stochastic gradient descent. The stochasticity. So normally we do gradient descent on the whole data set, but stochastic gradient descent, it takes a mini batch stochastic gradient descent. It takes a few samples, takes a batch of samples and trains your model. So when you have a batch of samples and you should be running on the entire data, what we say is that this batch of data, the gradient coming from this batch is basically equal to the gradient on the entire data set plus some noise. You can always write it in that form. So that noise is one of the factors which leads to regularization, better performance in deep learning models. So regularization by adding noise is a very big factor that plays into generalization in neural networks, and data augmentation is one of the ways you can do this. And this is what the trivial augment looks like. So if you have um, shear with a magnitude of 17, if you're applying a magnitude 17, this is what it would look like. If you had auto contrast, this is what it would look like, and so on. Now there's mix-up. What mix-up does is that it asks a slightly different question. It says you're introducing noise by adding some perturbation to your image, right, which is your input. But what if I also perturb the labels? Would that also improve performance? And turns out it does actually, and it's a very strong form of regularization. So the idea is that if you have two images, let's say xi and xj, what you can do is you can take lambda of xi plus 1 minus lambda of xj, where lambda is some parameter between 0 to 1. So what it does is basically it mixes the two images based on that proportion. And it does the same thing for the label as well. So lambda yi plus 1 minus lambda yj. Now you can see obviously the labels need to be from a different class. Otherwise, you would basically have the exact same value. And this is how you use this. Now, pay attention to the fact that you're changing the labels. So if you change the labels, what is going to happen is um, your output in the training during training is also going to change, right? So now you cannot calculate the accuracy as you would. So you have to do some changes there. But if you want to implement mix-up, this is how you're supposed to implement. You're supposed to use the collate function because you're going to change the labels as well. So now instead of having a 0 or 1 label, you can have a label, let's say 0.7 or maybe zero point 0.8 or maybe 0.1 and so on. And you train on this. Now, you would say that this is a little weird. What is happening? Why are you perturbing the labels? How is it performing better? Well, it turns out that there is a very old technique. I am forgetting the name of the technique. I think it's called, I think smoothing was label smoothing. Yeah, label smoothing was the name of the technique. So the idea is that in your data set, it's not necessarily that every single sample is correct. Okay. For example, I was doing some work recently and I found out that in the CIFAR 10 dataset, in the truck class, there is an image of two girls hanging out in a bar. They have been labeled as truck. Okay, so there are a lot of outlier images in datasets that are considered as benchmarks as well. So in that case, you cannot consider that the class truck is completely correct. There could be some amount of error there. Okay. So what label smoothing says is assume you have some amount of error, it's a 0.1, 10%, or maybe 0.01, some amount of error. Just subtract that from your labels. So you would have, so instead of saying this class is 1, you would say this class is 0.9. If this class is 0, you would say 0.1. So you're making the network less confident. And doing so actually improves the performance of the model because now it's not confidently incorrect on incorrect samples. So you can see where this idea is playing into mix-up. So mix-up also is kind of doing the same thing. It smooths out your labels and hence it improves performance. But this sort of regularization is very strong regularization. So if you're implementing this, make sure you run it for more number of epochs. And this is what mix-up looks like. So if you have the cat and a dog image, if you apply mix-up, this is what it will look like. And this is on the ImageNet dataset. If you have a cat and a dog, and if you take lambda to be 0.5, this is what the right image is what comes out if you apply mix-up. Now we come to cut mix. Cut mix is the successor to cut out. What is cut out? And this is the final augmentation that we'll talk about. So what cutout does is it takes your image, right, and then it removes a good
Atif, there
chunk
is a
of the
question.
image.
There's a
Okay, please.
question by Swayatta.
Yeah, yeah, just I think like I'm little not clear about one thing. Just wanted to. So when you say
Uh,
that you related label smoothing with the mix-up thing, right? So
mhm.
so when you're taking like the lambda xi plus one minus lambda, like lambda yi plus one minus lambda yj, won't it increase the number of levels also? Like if you are having a classification task, will it do that? I'm just little confused maybe.
So it doesn't increase it because in the classification task, what you're doing is you're trying to regress between 0 and 1, right? So let's say you have three classes. So you're trying to regress for each class. Let's say you're taking class 3, you have 0, 0, 1, right? For class 2, it will be 0, 1, 0. For class 1 is 1, 0, 0. This is your output vector.
Got it.
So you're basically
Yeah.
trying to regress up to that point. Now, what is going to happen is you're going to, instead of having 0, 0, 1 as your output vector, you will have 0, 0.5, 0.5 as your output vector. And you're going to perform,
Okay.
you are going to apply categorical cross entropy and learn accordingly.
Got it. So like it's normalized that way. Okay. Got it. Got it.
Exactly, exactly.
Yeah. Thank you.
Sure, sure. Okay, so cut mix. So what cutout does is cutout, it just removes a big bunch of pixels from your image. So it just makes it black. Okay. So if I can just show you the, okay, I don't have that image. Anyway, so what cutout does is it removes a big portion of a portion of the image and makes it black. Why do we do that? Well, the idea behind cutout was if the model is paying attention to certain areas in the network. For example, I'll just give you a quick example. If you remember that Arctic fox versus dog example, it's a very famous one. What happened, I think, around 5, 6 years back, this example came up, where these practitioners were training a deep learning model on Arctic fox versus dog data set. And what they found was the network was performing amazing, with 99% accuracy on the training set. But when they ran on the test set, it was failing miserably. Then they applied some explanation methods, and what they found was that the network was actually focusing on the white background because in every Arctic fox image, that image was captured on some snowy landscape. So the background was always white, and the network was trying to learn that because that was the fastest way it could classify that this is a dog and this is an Arctic fox. But during test time, there were many Arctic foxes that had been brought down to zoos, and uh, people were keeping them as pets, and they were being photographed in different household environments, and that is where it failed because the background had completely changed. So in order to make sure that this doesn't happen, you can do many different types of model related thing, or you could just in your data introduce cutout, or you can just remove chunks of the image. So now what is happening is that the network cannot focus on easy features. It has to focus on other parts of the image as well. What cut mix says is because mix-up performs really well, cutout performs very well, why don't we mix them together? And there arose cut mix. Okay, so it's very easy to publish papers in the deep learning field, and you just take these two things and mash them together, and if you get good performance, you're good to go. So what cutout does is it now has, instead of lambda on the input images, it has a mask. So this mask is basically the size of your input image. So if your image is, let's say, 32 by 32 cross 3, your mask would be a 32 by 32 by 32 matrix. Okay. And you would apply that matrix to each of your filters. Now, each of your channels, sorry. Now the mask, in that mask, it's either ones or zeros. So if there are certain ones, you will be taking from xi and the one minus that. So whatever was one is now zero and the remaining portion is one. So you'll be taking this part from one image and this part from another image. So that is how you get x cap, and y cap is basically here lambda is a percentage of pixels that you want to be 1 and 0. So if you have these many pixels as 1 and this many as 0, then you just calculate the percentage. So total number of ones divided by the total number of pixels, that would give you lambda. Or rather, you say lambda, and then that is how the mask is defined. And if you want to use cut mix, this is the code for it. You can just copy paste this code and it will run right now. And this is what cut mix looks like. So you take a dog and you take a cat image and you cut the cat face and put it on the dog. It sounds bizarre, but it works apparently. It works really well. And probably because of the reason that I stated. So this is this was basically all about the data augmentation. So if you have any questions, you can ask right now. Siddharth, are there any questions? I'm unable to see actually.
Mm, I don't see anybody raising their hands, but if there are questions, people can unmute themselves and ask.
Okay, sure, great. So we'll move on to model optimization. So in model optimization, so we talked about how you can massage the data to get better results. Now we'll talk about how you can change the hyperparameters or tune them so that you can get better model optimization, better generalization. And I know like you guys face a lot of issues. Like you start off with some learning rate, you change different values, you change the batch size, you change the architecture, you apply different layers, and everything has some effect on the model. And there's so many factors. You just don't understand what factors help you to get the best performance, or how do you reduce so many experiments down to only a few experiments that will lead you to the best results. So I'm here to help you out on that. Not too much, okay? I don't have too many tricks, but just a few which I believe can reduce your search space by some amount of workload. Okay, so we'll start off with learning rate and batch size. We know that if you change your learning rate, if you change your batch size, your performance changes, right? But so how do we change them in tandem? Normally, what I do or what I used to do was I would set some batch size, change the learning rate, right? And then during experiment, if I change the batch size slightly, I found, oh, okay, I'm getting better results. But then if I change the learning rate again, I might even achieve even better results. So the idea was like, where do we even stop? Okay. So this kind of answers that problem. So if you remember um, the equation, the gradient descent equation, what we have is W, which is the parameter vector, the entire neural network parameters. So T plus K. So if T is the time step here is the iteration number. So if you are running for 10,000 iterations, T is let's say 10 and K is maybe 20. So from 10th to the 20th iteration, that is the W that you're looking at. Okay. So WT plus K is equal to WT, which is the iteration at the 10th time step minus the learning rate, which is eta, into 1 by n. Here n is the batch size. Okay. And here we are seeing double summations and gradient of loss of x comma wt plus c. So what does this mean? What does this mean? I'll quickly make sense out of this. So this is going to be a bit of a problem, okay, to understand my writing. So my skills with paint is pretty bad. Just bear with me. So let's say we have wt, right? So okay, so wt plus 1. This is equal to wt, and then you have minus eta, right? And then you have the batch size 1 by n, and then you have summation over uh, your loss, your gradient of the loss, right? So loss because of x and wt. So this is what you have, and x basically belongs to some batch. I'm saying the gth batch or tth batch, whatever it may be, right? Now, if I do wt plus 2, so please be a little patient. It'll take a bit of time. So wt plus 2 is equal to, the same thing, right? Wt plus 1 minus eta 1 by n summation over the loss gradients. Now, remember this is wt plus 1 and we have already written the equation for wt plus 1 up there, right? So if I just replace the wt plus 1 equation, what I can write is wt minus eta, and then you have a 1 by n here, and then you have a summation, the gradient of this loss, right? And then you have again minus eta by n, and then you have a summation over gradient of this loss, again, some loss. Right? This is due to some other W. So what's happening is I can write this down as, if I take things common, then I can write it as Wt minus eta by n. And then you can see this part just becomes a summation, right? Summation over all the summations. Or if I write this as, let's say, alpha 1, so it's alpha 1 minus alpha 2 minus and so on. So if you take minus common, you get alpha 1 plus alpha 2 and so on. So if I just take that common, what I have is double summation over the gradient of the loss. And that's it. So this is how we come to this particular equation. Okay, so this is the equation. So basically summing over multiple time steps. Now let's imagine that instead of taking k iterations, what if I take a batch size of n into k? Okay, so instead of doing k separate iterations, I take a batch which is of size n into k. So you have that many samples. So let's say if you had n of 10, so you're taking 10 batches, a batch of size 10, and let's say k was also 10, you would be doing 10 plus 10 plus 10 plus 10, right? So you have 10 iterations, so total size is 100. So effectively, you saw 100 samples. Now let's say I take a batch size of k into n. So now my total number of samples that I'll be seeing is kn, right? So now instead of going from the tth iteration to the kth iteration, adding all my gradients, instead of that, I can just go from t to t plus 1, right? That's my next iteration, is just that entire batch. So w cap t plus 1 is just wt minus eta cap 1 by kn. This whole thing remains the same. And now there are double summation here. Why again? Because I'm saying that, taking a whole batch, instead of 10 examples, I'm taking an entire batch. So whatever gradient you get here can also be broken down and written in this form, a summation over all of the smaller gradients, because you'll be taking average anyway, right, of the entire data. So I can also write it as a summation. So that's what is happening here. Now, if we assume that gradient of the loss of x with respect to wt plus j, so the last gradient is equal to gradient of loss of xwt. So basically, if you look at the can I highlight? Okay, I have a pen. Okay. So if I look at this part, so if I just essentially say that these two parts are the same, right? Then what I can do is, if I set eta to be eta into k, eta cap, right? Then this thing becomes equal to this equation, correct? Right? K gets cancelled out, and then you have minus eta by n, and these two things are the same, so you essentially get the same equation. So if that were the case, and this is a very strong assumption to have, that the gradient with each iteration, after you perform the gradient descent after all these iterations, and the gradient that would come from this entire batch, both of them will lead to the exact same spot, is a very strong assumption. Why? Because you're taking different samples, right? You'll be permuting or shuffling your data. So it's very unlikely that you'll be having the exact same 100 samples. But turns out that if we assume that this is true, okay, if this is true, then what I can do is I can just scale my learning rate according to my batch size. Correct? So if I want to get the same amount of performance that I would get if I would take batches of 10 and do 10 iterations, I can do that with a single iteration with a batch size of 100. But now my learning rate has to be also adjusted. So whatever learning rate I had should be into 10. So linear scaling. Okay. And this works very well in practice. So what do we do here? The idea is that if you didn't understand any of this, no issues. I'm just giving a simple message. The message is fix it, just fix any learning rate and batch size. And normally, smaller batch sizes lead to better results. So just take a small batch size, 64, 128, 32, whatever you prefer, and try to set a learning rate for that. Once you are done, now linearly scale. So if you're multiplying a batch size by 2, multiply your learning rate by 2 as well. And do this until you have a sufficiently large batch size and your network's performance is not degrading. So you can guarantee that you can achieve the same performance as you would with a smaller batch size, but now much faster because the number of iterations is significantly reduced. Okay, so this will help you in speeding up your experimentation process. Now, so there is no code for that. This is something that you just need to look at by yourself. Now we come to weight decay. Okay. So what is weight decay? Weight decay is just this. So if you have a gradient at the time step t, so G here is the gradient of your network. Okay. So if G is the gradient and theta is the parameters, then all I'm doing is I'm multiplying a lambda factor to theta. So if you remember when you write code, you in SGD tosh.nn.optim.sgd, I think something of that sort, we pass the model dot parameters, and then we pass the learning rate, we pass momentum, and we also say weight decay equals to some 5e to the power minus for some value. So that value just directly gets multiplied to all of your weights in your neural network. So people have, and if you go to, and I looked at this on the internet, if you look at some blogs, they'll confuse weight decay with L2 regularization. It's not their fault because if you look at L2 regularization, it kind of looks like this. So y cap minus y, you have whole square, and then you would have, let's say, 2, uh, and you have, okay, uh, plus, and then you would have some lambda here, and then you will write, god damn it, 1 second, eraser, okay. Huh. So, so you would write lambda into, we have theta, so we would write theta t minus 1 transpose theta t minus 1, right? So this is what you have. Now, those who are not familiar with this is just a mean squared error, right? With this L2 norm regularization. Why am I calling this L2 norm regularization? Because if you just take two vectors, theta t minus 1 and theta t, and if you apply the dot product, what you get is basically this value. So you get theta t minus 1 square, L2 norm of this. Okay, this is what you get. You can also check this out. So each value is just being multiplied together. So you have theta, let's say theta 1 into theta 1. So you get theta 1 square plus theta 2 square and so on. So this is what the L2 regularization looks like. Okay. So now if I just differentiate this, what do I get? I get y cap minus y, and the 2 gets cancelled out. And then you will have you have some like del y cap by, you would have del theta t minus 1. I'm not writing the t. And then plus you would have theta t into theta transpose into theta. What you get is basically lambda theta. So you can see if I treat this as the gradient, right, g, and then I have plus lambda theta. So you can clearly see my gradient, if I perform L2 regularization, is exactly the same if I would perform weight decay. And in what PyTorch does is that it will just multiply this lambda with your parameters when you're saying that you want to use L2 regularization. And this kind of leads to, because this is efficient, right? You don't need to actually go and calculate the gradient. If I already know what the gradient is going to be, I'll just do that. So they directly multiply this lambda parameter to all of your parameters in the network if you say you want to use L2 regularization. So that is one of the major reasons why people say, okay, so weight decay is the same as L2 regularization, but it is not. And where do we see this? Where do we see this change? If we apply the Adam optimizer, so for stochastic gradient descent is fine, but for Adam optimizer, because the parameter values are changing, uh, the way the differentiation takes place is different. Sorry, so the differentiation takes place, right? And then you would get gradient plus lambda theta, and then you have a few different momentum factors where the thing gets clubbed together. Now, if you directly multiply lambda here, or if you would multiply lambda after finding out all those momentum terms, these lead to totally different results. And this is what people found out. So if you take weight decay, if you apply lambda, it gets clubbed with the momentum factors. If you apply L2 regularization and take and use atom, then your this lambda parameter does not get clubbed with the momentum factors. Okay. So the some of the deep learning practitioners they found this problem out and then they proposed a new optimizer called Adam W, and that was the entire reason why Adam W was born. Okay, so how do I remove this? Okay. So what is the issue with applying? Okay, so this was the whole picture behind the difference between weight decay and L2 regularization. Why Adam W was born, weight decay is, and so on. Now the question is, and this is where all the people are making an error in their code right now, is if you're using SGD or Adam or whatever, and if you're applying weight decay right now, your code is faulty and you're not achieving the best possible performance that you could possibly get. Why is that the issue? Take a look at this graph. Okay, you have a bunch of samples between the range of 800 to I believe 1400. Okay, and they are very nicely uniformly distributed across 0 to 1000. And this is very exaggerated example, but this is basically I'm performing regression, right? So what is happening is this dashed line is the bias without regularization. Okay, so what would it look like? So it would look like so the bias without regularization looks like this. So let's say you have W naught plus W1x. Okay, this is your output. This is your equation of a line. So what I'm saying is normally you would have, this is, we call it y cap. You would do y cap minus y. So you would do y cap minus y, right? Whole square plus, and then if I do just w lambda into w1 square. I mean, if I had, let's say w1, w2, w3, then I would write w1 square plus w2 square plus w3 square. But right now, okay, I'll just write it down. So you can have w2 square. So this is basically the L2 norm, correct? So you have something like this. If you add w naught here, okay, if I add w naught here, you can see what happens to this solid line. You can see it is unable to move away from the origin. So whenever you have this set to 0, so just let's say you have W naught set to 0, you're assuming that your model is passing through the origin because if this, this is your, let's say this is the axis, you're making sure that the model only passes through the origin. If you add a bias parameter to it, which is W naught, you basically allow the line to shift. That's the whole point of the bias parameter, to allow you to shift your line. Now, if you set this to 0, you're basically constraining or assuming that your model always performs, the solution of your problem passes through the origin, which is incorrect, right? You cannot just assume that. And you can also try this. If you can set the bias to 0, you won't get very good performance. Maybe you can, maybe you won't. There's no guarantee. but it's best to let the network learn. So if the network knows, if the data set requires the bias to be set to zero, the network will learn the to set the bias to zero. And if it's not, then it'll set some value. So if you do not add, so here what I've done is I've taken a very large W, extremely large. So this is a very exaggerated example. What would happen is that this solid line will slowly move towards, very slowly, but surely it will move towards the same dashed line that we have here. But it'll take a lot of time. Rather, if I just allow the buyer, if you don't put that lambda, don't put my W naught into uh, this L2 regularization, I will actually be able to achieve the same performance, but like in 1 or 2 epochs, as you can see here. So how do we fix this problem that we have? So every PyTorch implementation right now has this issue. So how do we fix this? You can just copy this code. So what this code is telling you is that you have two separate sets of groups. You have a decay group and a no decay group. In the decay group, you'll add all your weights, all the weights of all your parameters. In the no decay group, you will add all the biases. And if you have a batch norm or let's say layer norm, you don't want to add the gamma and beta parameters, which you have for batch norm, into your decay group. You don't want them to decay as well because those are scaling factors, right? And if you don't want to apply L2 regularization on them, because if you do, then your scaling becomes extremely slow. Again, your network becomes very slow to train. So you don't want to do that. So just leave the batch normalization or all the normalization layer parameters as is, just and the bias parameters of all the layers, just apply L2 regularization on the, or sorry, group or weight decay only on the parameters or the weights. So this is the entire code. Now coming to batch norm and learning rate. Okay. So when you're using batch norm, what sort of learning rate should you keep? Okay. The idea is that okay. So any questions for now? I hope I'm not rushing.
No, you're making good time. If anybody has any other questions, please you can ask them or you can put them in the chat box as well. I can read them out. Okay, doesn't look like we have any questions. Maybe you can continue.
Okay. Either my talk is super boring or everyone is understanding everything. I hope it's the latter. Um, okay, so coming to batch norm and learning rate, where do we set how do we set the learning rate when you have batch normalization? Okay, so there is this derivation, okay, and I have this derivation here. So I did this derivation on board. Um, if you want, you can look into that. I won't be going into this right now. It's elegant, it's not messy, it's very elegant, but it'll take time. So rather, let's focus on the result. It's actually, it shouldn't be two. I don't know why a lot of deep learning theory, they say, eta is less than 2 by lambda 1. Rather, I feel it should be eta is less than 1 by lambda 1. There's no magic number. I don't know. Deep learning has this fascination with magic numbers. Set momentum to 0.9. Why? I don't know, but it works really well. Okay, so it has a lot of fascination with these magic numbers. They did this in the derivation as well. And I don't think it's really required. You can just write eta is less than 1 by lambda 1. What is lambda 1 here? What is eta? Eta is the learning rate. Lambda 1 is the eigenvalue, the maximum eigenvalue of the Hessian of the loss with respect to the parameters. What does that mean? So I'll just quickly give you an overview of what the Hessian is. First, let's try to understand what differentiation is. Okay, when I write del y by del x, what does it mean? I'm saying for the small change in x, what is the change in y? That's what I'm saying. So if I move slightly, if I move my x very small amount, infinitesimally small amount, I want to see what effect that has on y. Okay, so this is what del y by del x means, dy by dx, whatever you want to say. This is what gradient means. Now, if I do del 2y by del x square or d2y by dx square, I'm doing a double differentiation. What does this mean? Make a small change in x. Okay. Now, for this point, again make a small change in x. So you're making infinitesimally small changes. Now let's say you have two parameters, theta 1, theta 2, and I do del y by del theta 1, del y by del theta 2. Uh, del 2y by del theta 1, del theta 2. Okay, so I'm differentiating y. First, I'm differentiating y with respect to theta 1, then I'm differentiating y with respect to theta 2. What does this mean? This just means do del y by del theta 1 first. So you made a small change in theta 1. So you moved it, let's say, from here to here. And then you observe the change in y. And then you're doing del y by del theta 1, del 2y by del theta 1, del theta 2. So now you're saying you have moved with respect to del theta 1, now keep it fixed. Now move in with respect to theta 2 and now see what the change is in y. Okay, this is basically the idea behind double differentiation. So as you can imagine, if I have all my parameters, let's say theta 1, theta 2 up to theta n, and then I start taking differentiation, let's say I differentiate theta 1, theta 2 with respect to theta 1 and theta 2, with respect to theta 1. So I'm differentiating del y. Okay, so I'll just quickly show you an example out of this. So let's say I have theta 1 and theta 2 as my parameters. Okay. Then I want to perform double differentiation with respect to both of these parameters. And let's say j is my loss function. Then I would write del j, del 2j by del theta 1 square, right? So I double differentiate with respect to j. What are the possibilities do I have? The other possibility is del 2j by del theta 1 and del theta 2. Okay. Now similarly, I do del 2j by del theta 2 and del theta 1. So I'm differentiating with respect to both theta 1 and theta 2. And then this is again del 2j divided by del theta 2 square. Right? So now, as you can see, I can write this as a matrix in the form of a matrix. This is a 2 by 2 matrix. And as you can imagine, differentiation is a linear operation. So whether you do del j, del 2j by del theta 1, del theta 2, or you write del 2j by del theta 2, del theta 1, it's the exact same thing, right? So this is a symmetric matrix. So this is what we call the Hessian. This is the Hessian of the loss. So the Hessian of the loss with respect to all of the parameters. So what does this H tell you? It's going to give you some information, right? What is it giving you? Well, if you think about it, a gradient, what does a gradient tell you? When you perform differentiation, you're saying a small movement in one parameter, what effect you're getting in the output. So the gradient basically, and in other ways, you can also think of the gradient as, you have seen this example a lot, it's just a tangent. So at this point, you're making a small change. What is the change in the function? Well, the gradient tells you the slope, right? It tells you what is changing. So if you remember the slope formula, you have y2 minus y1 by x2 minus x1 if you're given 2 points, right? Now, if you differentiate, what am I saying here? When you write del y by del x is small change, right? So x2 minus x1, very small change, a del x that you write. And you're observing what change you're having in y. So y will give you something. So y2 minus y1. So you can see you can also relate it in this way that the slope is being calculated because when you write del y by del x, small change in x is small change in y. Or effectively you're writing y2 minus y1 by x2 minus x1. So that is why gradient is known as the slope. Okay. So now you're getting the slope. What does Hessian tell you? Hessian tells you that at this point, if you just look at this row, it's telling you if you make small change in theta 1 and then make small change in theta 2. If you had, let's say, theta 3, then you would have small change in theta 1 and small change in theta 3, right? And so on. If you keep doing this, then you do this for the next one and the next one. So you can see that at the current point, it's actually telling you your local neighborhood. It's giving you information about the local neighborhood. So it's telling you what your function looks like around this point. So around the current point, if I differentiate in all directions according to my parameters, I'm going to understand what is this surface looking like. And Hessian is and that is why Hessian is an extremely important aspect when performing optimization. Because when performing optimization, it tells you what your surface looks like currently, the local neighborhood. So instead of taking a gradient, like a step in the direction of the gradient, you can actually use the Hessian to better understand your loss surface and move accordingly. Okay. But obviously, you can imagine if I have theta 1, theta 2, I have a 2 by 2 matrix. If I have four parameters, I have 4 by 4 matrix. If I have a million parameters, which is very normal in deep learning, let's say VG16 network, outdated by 10 years now, it has about, I think, 14.7 million parameters if you do some reduction on the CFAR10 dataset. So that's 14.7 million cross 14.7 million matrix, which I mean, it's not possible to compute. And this is why we cannot use Hessian in deep learning. Otherwise, we would have had really good results. So we cannot use Hessian. Rather, we are using an approximation, which is gradient. Now, if I compute the eigenvalues of the Hessian, and I'm not going into what the eigenvalues of the eigenvectors mean, I am assuming you already know that. If you look at the maximum eigenvalue in with respect to the Hessian, um, this is very controversial. So my math prof is really going to scold me if I give you this intuition. But just take this idea that if if this is your surface, right? If you have a surface, this what the Hessian is telling you, and you are at some point here, the maximum eigenvalue will tell you the direction or the sorry, not the direction, but rather the magnitude of the drop or the incline, whatever it may be. So it's telling me the magnitude of the curvature. Okay. And my math prof does not agree with me on this. He says you can't just arbitrarily say that. But just to understand, for understanding purpose, the maximum eigenvalue tells you what your curvature is. So let's say if I'm at this point, my curvature is pretty large, right? I hope you guys can see. So it's pretty large. Um, so the maximum eigenvalue it will be very large here. But let's say if I reach at this point, this is a very almost flat surface. So the eigenvalue is going to be very small. Okay. So what batch norm does is, I mean, let's put aside batch norm for now. What happens is that during training, if if you're going to somehow what this eta is less than one by lambda one means is that if you take a step larger than this one by lambda one value, right? So if this is very sharp, okay, the one by lambda one will be a very small value. And if you take a step greater than that, so lambda one is telling you this is the entirety of the step that you can take. And you're saying, I'm going to take a step bigger than that. And you don't know what's happening here, right? This could look like this. So you took a step this way. And then if you took a larger step, you might actually reach here. Or you might actually, if you take a very large step, from here you might go this way and go out. So you might overshoot. So that is why it's very important to make sure lambda eta is less than 1 by lambda 1. And if you look at the values of lambda 1, if you have this luxury of having a very large cluster and CPU GPU cluster, and if you run this for days and days on a neural network of arbitrarily medium scale neural network, you can actually calculate, brute force your way out and calculate the Hessian and then calculate the eigenvalues of the Hessian. And if you look at the values, you'll find that the Hessian is between, let's say, 60, 70. It's always pretty like a large value, like 100, 200, and so on. Okay. And the value over time reduces. So if it starts off from 100, they'll keep reducing. And so reducing meaning you're going from a sharp point to what do you call it? A flatter region of the surface. So if you that's the whole reason why we set learning rate less than one. Okay, so we said 0.1, 0.01. That's where the thing comes from. That if you divide 60 or 100 by 1, you get 0.01, right? And that's the reason why people said learning rate, these are the values for learning rate. So it's not exactly magic. It has strong mathematical background, but you'll have to really dig into it. So that's the reason why we set learning rate to be 0.11. So clearly we want to set the learning rate to be less than 1 by lambda 1. Oh, sorry. Now what happens is this paper, this Pachnom Santurkar et al. Paper, what this says is that this lambda 1, batch normalization reduces lambda 1, the value of this, it reduces the value of lambda 1. And if it's doing that, now instead of, let's say, if lambda 1 was 10, you would have a result of zero point 0.1. So it has to be less than zero point 0.1. But now let's say lambda 1 is just 1. Okay, it's reduced. So it has less than 1. So now you can actually use a larger learning rate, and larger learning rates have been shown to have a lot of performance benefits like regularization and also letting you achieve your preferred goal on the training loss much faster as well because you're taking larger steps now. So it's always preferred to have a larger learning rate. And turns out that the entire power of batch normalization comes from the fact that it reduces lambda 1. So if you're going to use batch normalization layer, let's say you have a network and you apply batch normalization, the whole power of batch normalization lies in the fact that it allows you to use a larger learning rate. In itself, it will not have much effect. But if you now start using larger learning rates, which batch norm allows you, you will get much better performance. Okay, so that's the whole point. So now if you in your take home messages, if you didn't understand any of that intuitive maths that I was talking about, if I bored you to hell, just take this message home that when you're applying batch normalization, make sure to increase the learning rate because that's where the advantage lies.
Hey,
Secondly,
I had
this
one
is
question.
yeah.
So, when you say increase the batch norm with the learning rate, is there any is it like linearly you mean, or
No, there is no linear scaling here. So we don't know. What you can do is just increase the scale. So people have observed that if you're using, let's say, 0.01 as your learning rate, then you can go up to zero point 0.1 as well. So you can do into 10 and see what results you get. But mostly you should increase your learning rate.
okay? And the paper that you mentioned, so there they have like given this whole proof, right? That
Yeah.
it's related with the eigenvalue and
Yeah, the whole proof is there. If you want the proof to why the learning rate has to be bounded by the eigenvalue of the Hessian, you can get it from here. This is what I've done. You probably won't get it in any paper because they assume this basic knowledge. I don't know how they assume this basic knowledge, but anyway. But if you want to find the proof of how batch norm is reducing lambda 1, then it's in the paper that I have referenced.
Yeah, one question.
Mhm.
So you said that calculating Hessian on a very big problem, like the very big network, would be a problematic, computationally inefficient. So like, can Hessian be calculated on a batch of weights or a batch of parameters? And so creating a loss on the whole weights and calculating on like batches of weights. So you can calculate the loss and convert
Yes.
the gradient on batches.
Okay, so you're saying on the batches. Okay, so the problem with batches is that, as I talked about, the local neighborhood, right? So you get the local neighborhood information only when you take difference, if you differentiate, let's say with theta 1, with all of the parameters, right? So you get the idea of how all the other dimensions. So remember that each theta is a dimension. Okay.
Yeah.
So let's say I have theta 1, theta 2, theta 3. I have three dimensions. So if I want to understand the local neighbor, I will have to take theta 1 differentiate with respect to theta 1, then with respect to theta 2, then with respect to theta 3. So all I'm saying is that if theta 1 is my x-axis, I have theta 1 here. What is the change that will happen in the
Atif,
y-axis?
your voice is not clear. Can you come closer to the laptop?
Okay. So is it audible now?
Yeah, yeah, it's okay.
Sorry. Sorry. If this is the x-axis, you have theta 1 here. Then small change in theta 1, you want to see how your x and y axis are changing. Similarly, you do that for the y and z axis, then you do for the y axis, then for the z axis. Then you get this local. 3D ball, a sphere of the surface, right? If you're saying, okay, let's say just theta 1, theta 2, right? Not look at theta 3. Then you're missing on the surface is changing in certain
I think
direction.
I
Effectively
think
that Z
still the audio issue is there. Uh,
um, is my
Maybe the other guy,
Can
he can go
everybody
on.
else mute themselves?
Yeah.
am I or is it better now?
Yes, yes.
Okay. So the idea is that if this is your x-axis, you make small changes in theta 1, right? And then you make small change in theta 2, theta 3, and so on, x, y, and z axis. Then you get some information about how the other dimensions are changing with respect to one dimension. Now you need to do this for the remaining two dimensions as well in order to get the entire picture of this sphere. Okay. But if let's say if you take a batch of size 2, so you're saying ke theta 1 and theta 2 only, not theta 3, then you're missing out on information about the how the surface is changing in that dimension. So now you have incomplete information. And if you have incomplete information, it will lead to disastrous result. So it's as good as so I might as well instead of doing all that effort, I might as well just uh, take the gradient because it's good enough.
Yeah, yeah,
I hope is that clear?
yeah, clear.
Your voice is dropping actually. I can't. Siddharth, can you hear him?
Yeah, he said that it's clear, so you can continue.
Okay, okay, okay. So just this is the last slide, so I'll make it quick. So you might have heard about schedulers. So schedulers have been used in many different parts of
You have
the.
one question from Zeel Patel.
Okay.
Yeah,
How
so
do I
I wanted to ask that, like as you explained, that batch norm can help us have the lower maximum eigenvalue. So do
right?
people initialize the weights in a way so that in the beginning itself we have a very small maximum eigenvalue?
People have not explicitly done that. There are a few papers that try to approximate the Hessian because first of all, if you cannot find lambda one, then you can't do anything about the initialization. But you can approximate the Hessian using FIM, which is Fisher Information Matrix. Okay, so if you approximate the Hessian, then you can. And it's a very fast way of computing FIM. So once you compute FIM, you can. What people do is they run like one or two iterations, use the information available through FIM to get to a point where the maximum eigenvalue is very small. And then they say this is a point of initialization. From here, you can start your optimization process. So they take one or two steps to get to a flatter minima and then start from there. That's your initialization. So people do that. But also it turns out that if you use first order information like gradient and let's say variance or mean and variance, right? Mean and variance information. So instead of doing second derivative, if you just look at the mean and variance, turns out that if you try to set them properly, which is what a lot of the famous initialization methods like K-mean, Javier, they do that, then you tend to actually reduce the maximum eigenvalue. This has been seen. So yeah, there are people taking this lambda one into account. In fact, if you look at ADA Hessian or ADA grad, these are second order optimizers, second order approximate optimizers. They actually take this information into account. What is the maximum eigenvalue? They approximate that. You can use power iteration method to very quickly approximate lambda one. So they take that into account and try to do optimization. And they actually perform much better when there's a lot of non-linearity in your data.
So for all these methods, we would have to like at least compute at least one step or two step of the training, right?
Right.
Okay.
Because there is no closed form solution for neural networks. So you can't exactly know if you make any change here, What is the change that is going to be in the output? You don't know that. If you knew that, you could create an initializer accordingly. But that is why you need to take a few steps and then make sure these steps lead to a smaller lambda one. I hope that
Yeah,
answers your question. Okay, okay. So, what is the idea behind schedulers here? The idea is that this is a very amazing idea. I felt like when I discovered it for the first time. Um, During training, so I was doing this experiment where I was trying to see what happens. I don't know. I was tracking some metric. I think it was how correlation, yeah, neuron correlation. So it turned out that during training, like at beginning, the neurons are not correlated, but as they keep training, a lot of the neurons start getting correlated. Okay. So if you apply dropout, okay, one way is to stop this correlation problem is apply dropout, so that each neuron will learn something else, and therefore you get better representation, and therefore that is why dropout performs much better. But here is the thing that if you take dropout and apply very small amount of dropout at the beginning, but more at the end, you get even better performance because now you're dynamically restricting this correlation issue. Okay. Similarly, you have weight decay schedulers. So instead of weight decaying across the same with the same value across the entire training period, maybe change it because your gradient step is changing, right? Similarly, we have learning rate schedulers. This is very important. So how should the learning rate evolve over training? Now, if you remember, what is happening is with this curvature, the curvature is becoming smaller and smaller, or basically your gradient is becoming smaller and smaller. Okay, as you train. So you're reaching a flatter minimum. So what you want to do is you want to take large steps when when your gradient is large. Okay. And obviously you not need to make sure that eta is bounded by 1 by lambda 1. You can't make sure that. One way to do is trial and error. So just find it out. So, or there's another way, and I'll tell you, and that is where scheduler comes into play. So you keep moving, right? You take large steps at the beginning and then small steps at the end. So you have large gradient, then small gradient. So take smaller steps at the end so that you don't overshoot your minimum. That is how you want to change. So how do you solve this problem? You can use something called cosine annealing. And there are many different learning rate schedulers, but what I found personally to be the best is cosine annealing learning rate. It looks like this. So the idea is you start off with some learning rate. Okay. So you start off with some learning rate, and as if you remember the cos diagram, it starts off with 1, I think, and then it goes down to 0, then reduces down to -1 and goes up and so on. So what cosine annealing does is takes that first portion of cos function, and let's say you start off with 0.001, right? This is your learning rate. You slowly, smoothly reduce your learning rate down to whatever minimum value you have set. So this is what it looks like. You have T max, which is the number of epochs. Remember in PyTorch, if you go to the documentation, they'll write T max is equal to iterations, but that's not the case. It is actually number of epochs. Okay, so if you're running for 200 epochs, just say that I'm going to run for 200 epochs. So cosine annealing, what it'll do is it will adjust the learning rate drop between the first iteration and the last iteration such that you start off with the learning rate that you give and then it reaches the minimum learning rate that you have set. So this is what the code looks like. So if the maximum epochs and eta min is the minimum amount of code, minimum amount of learning rate that you want to set. And doing this actually gives a very big boost in performance. So make sure that you're using schedulers. Finally, this is very hand wavy. I don't have any theoretical backing for any of this. This is what I have observed from like running many experiments. This is what I've observed. You can or cannot use these recommendations. So what I found personally is that if I have a smaller batch size, SGT with momentum performs really well for vision tasks. For language model, ADAM-W performs really well. And if you have a larger batch size, then this LAMB optimizer works really well. And that's about it. Yeah, that's it. Thank you. Any questions, anyone?
Yeah, so we're now open for questions. If anybody wants to ask Atif any questions, please go ahead. He's also part of the Slack channel, so you can ask him your doubts there as well. And he will be sharing the presentation and will be uploading a video as well. So you can connect with him after that.
Yeah, I have an off. Yeah, I mean, I have an off-topic question. Maybe I can ask it later after others have.
Yeah, sure, sure. Tejas, you can go ahead. You can ask.
Hello, Atif. I actually
Hmm.
had one question regarding to the learning rate and batch size correlation that you mentioned. I
Mhm.
just want to clarify one point. I think you mentioned that increasing batch size might degrade performance in general. Is that really true? I mean, if I increase the batch, I mean, if I just, I mean, uh, input the entire data set all at once, ideally, shouldn't that give me a better performance? Like what we say is that the mini batch gradient is like an estimator of the true gradient, right?
Right, exactly.
So, I
So the
mean, if I
problem
increase,
here is that, yeah, so as I talked about this, you gradient descent should actually be performed on the entire data. Okay. But when we do mini batch stochastic gradient descent, we are basically taking a small gradients. We're calculating the gradient on a small batch of data. So you can actually say that if you look at the entire data set, if you take the gradient there, that gradient can be written as, let's say if I call that G and the small batch as G dash, then you have G is equal to G dash plus some epsilon, some error, right? So that's where the estimation portion comes into play. So it turns out that this epsilon, this noise that you have, this noise actually helps in regularization. And there are a few papers that actually talk about this, that because of this noise, you actually achieve better regularization. Now, I know there is another paper, I think by Tom Goldstein, which says that you can actually train on the entire data set. So like take one batch is equal to one whole data set and you can still achieve similar performance. Okay. And I'm not quite sure why that happens. Because we have observed, and there are a lot of theory that has shown that uh, this error, this noise this perturbation is actually helping us improve the regularization of the network, which leads to better generalization. And it has also been seen that if you personally, I've also seen that if you have if you look at Resonate 18 and running it on CFAR 10, you probably get very good results with patches of 128. But if you start increasing 256, 512, 1024, you'll see a slow reduction in performance, assuming that you're running for the same number of epochs.
I just need a clarification. So, the performance we are talking about is the generalization gap, right? Like between the test and train, or is it performance on the training side?
Accuracy. I'm just directly talking about the accuracy, the test accuracy.
Okay. Okay.
Anyone else? Okay,
Okay,
so
if no one has any question, I'll go ahead. So,
yeah, sure.
like, yeah, so basically, I like finished my MS in a year back, and then I joined industry. So, like, what I'm seeing is with this LLMs and everything, like a very large models are taking like a lot of precedence when it comes to performance, accuracy, and whatnot, and with lot of increasing compute, more performance like that. So I mean, where does it leaves the academic research or like what we used to have before, like pre-training from scratch, that things. Where does it what do you think, like what are the scopes on that regard, uh, regarding this research and like anything like in AI in general?
Yeah, so this this problem is being faced by a lot of my friends as well. Even we sometimes get discouraged, right? Seeing that uh, there are these large models and they're performing amazingly well. So, what is the point of my research? I mean, most of the research that is happening out here, they focus on, I think, all in India, a lot of this, in a lot of institutes, people are focusing on trying to improve achieve SOTA. It's also the case in other institutes as well. And when you just come across a model like Llama 3, right? And if you just take the feature representation of Llama 3, you get SOTA performance. So what do you innovate there? What happens to research? Well, the thing is, you go backwards. Okay, so Jan LeCun also talks about this. They say Jan LeCun is very strongly opinionated on LLMs. LLMs, what is an LLM? Is just next character prediction model. That's it, right? It's just learning what the next character should be given all of these past characters. That's all LLM is. So it is hallucinating, it cannot reason, it cannot do anything. In the industry, people will say that AGI is coming and this and that. None of that is true. But personally, that is my opinion. Because if I look at LLMs from the first principle, none of that is true. Okay. So it is all you're doing is just learning a probability predictor, and it's going to do that. Now, if you give cite some examples where you say that but LLMs can reason, well, they cannot because there is a very simple example about a man, a boat, and a dog, something of that sort. It's an impossible task. Very simple. If you look at it, you'll answer it within a second. Carry, this is not possible. But an LLM cannot because that was probably not available in its training data. So LLMs are not able to reason. So you have that entire reasoning discipline is open. LLMs are too large. So now you have this problem of how do you fit this performance of LLMs on smaller and smaller hardware, which is kind of what I am working on, which is model pruning. So there are a lot of open areas and research that you can still work as long as like mainly people don't understand how neural networks work. So as long as you're not trying to beat SOTA performance, but rather trying to understand how neural networks work from a first principles perspective, you're pretty much good.
Yeah, I mean that's a great answer. Yeah, I mean, yeah, I mean this interpretability and all these areas.
Exactly.
Yeah, I mean they have to take. I mean that's where we go now, I guess. Yeah.
Exactly. I mean, even in your industry as well, I believe, like for a lot of problems, you might be using gradient boosting machines still, right? People don't want to use neural networks that easily because first they lack the hardware. Secondly, where is the explainability?
Yes, yes, correct. Yeah, at least yeah for traditional ML problems, it is the case. Yes, even in
Yeah.
industry. Like,
Yeah, as long as your data is not unstructured, I mean structured data like tables, time series, and so on, as long as you don't have to extract features like vision or audio or text, uh, traditional machine learning is pretty good. Any other questions? Okay, so if no one has any
Okay.
questions,
Yeah.
I have
So I
one
would
question
like
for it.
yeah. Okay. Sure. Please go ahead.
How was the talk? Like, I would like some feedback. Obviously you can post that feedback in the Slack group. I'll definitely answer to everyone personally. But just if anyone wants to say anything, what can I improve in my talk? I would be really glad to hear it.
so personally, I use this talk as a refresher for my like basic deep learning certain areas actually. Like I saw this because it's been a year actually since I've been here. So I saw this slide and I mean the title and but it was more much deeper than that to be fair, and it will
Okay.
uh, really good and like, would like to see you again here. Definitely. I mean, this
Oh,
is my
thank you
first
so
time I
much.
joined here. So, yeah.
Oh, okay, okay. That's great. That's great. Thank you so much. Sure. Siddharth, you were saying something. Yeah, please.
Yeah. So no, I'm just saying that if there are no more questions, then I would like everybody to thank the speaker for giving us a wonderful tutorial and to everybody else as well for joining today. Thank you so much. I will now stop the recording. Uh, yes. So we can close off.